The Pythagorean trig identities, where do they come from? Well, it starts with an idea that we saw of parametrics. There's my circle. I'll give it radius of 1 for convenience. And I could come up with parametric equations for any point on that circle. Now we know the equation of that circle, of course, is x squared plus y squared equals 1. So I could create parametrics, the parameter being the angle that's being formed at the centre of the circle there. So y would be the sine of theta, because I've made it a unit circle. So it makes life easier, y over 1. And cosine theta. So there's one way I could describe it parametrically. X equals cos theta, y equals sine theta. But as I already know the equation of the circle, I could substitute those parameters in and I get the first of our trig identities. And so this is why they're actually called the Pythagorean trig identities, because essentially if you look at it, it comes from Pythagoras. X squared plus y squared is the hypotenuse squared. The sine squared plus cos squared equals 1. Now what we do is we get that identity and say, hey, let's divide everything by sine squared. And if we do that, well, sine squared on sine squared obviously becomes 1. Cosine over sine is the same as cotan, and 1 over sine, well, the reciprocal of sine is cosec. And we get the second of our trig identities. 1 plus cot squared is cosec squared. But instead of dividing by sine squared, say I got that first one and divided everything by cos squared instead. Then we get sine on cos, which we know is tan. Cos on cos becomes 1, and the reciprocal of cos is of course sec. And we get the third of our trig identities. So essentially they are the 3 Pythagorean trig identities. Sine squared plus cos squared is 1, 1 plus tan squared is sec squared, 1 plus cot squared equals cosec squared. The other thing that comes in handy, it's not a Pythagorean trig identity, but it is a nice relationship. And I in fact used it to go and show some of these, that sine divided by cos is the same as the tan ratio. So that's just a relationship that can come in handy as well. So the sorts of questions. Now, the first example I give here is one where actually I wouldn't use a trig identity to do it. But often you see them ask this question with trig identities, because what they're expecting you to do is to go, well, I know sine squared plus cos squared is 1. So if cos theta is 3/4, I know cos squared is, what would it be, 9 on 16. I could then work out what sine squared is, so then I could work out sine, and tan is sine on cos, and but they've told me tan's negative, so I know which quadrant. A lot of work. To be honest, it's a lot easier to do this question this sort of way rather than using the trig identities. Simply draw myself up a triangle. They've told me cos theta is 3/4, so I know adjacent over hypotenuse 3 and 4. Bit of Pythagoras, I've got the other side. Now they've told me tan theta is negative, but they've also told me, without explicitly saying it, that cosine is positive. So I know I must be in the 4th quadrant. Tan's negative, cos is positive. That's therefore telling me the sine ratio must also be negative. Read it off the triangle, root 7 on 4, got the answer. I think a much quicker, more efficient way than using trig identities for it. Alright, well, let's look at examples where we actually are using our trig identities. The first one, again, I probably wouldn't do all the working out that I'm about to do here. Hopefully we would just look at that and go, oh, 1 minus cos squared, that's sine squared. But I'm using this to illustrate the idea. If I want to simplify this, and I'm going to use trig identities, the nice thing about our trig identities, you'll notice, is no ratio appears in more than 1. So you can't pick the wrong one to use. There's only one you're going to use. So cos squared, the only one that I could use would be the one that says 1 plus sine squared is cos squared. So if I substitute in, and I know it seems a really stupid thing to do, because if I realise that cos squared is 1 minus sine squared, why wouldn't I have just realised 1 minus cos squared is sine squared? But okay, I'll substitute in the 1 minus sine squared for cos squared, play around with it. Oh look, we get sine squared, there it is. Okay, I wouldn't be doing all that working out. But that's the idea. I'm looking at them and saying, oh, which ratio could I use? So again, sec squared minus tan squared. Oh, not sure what that is, but I've got this trig identity that says sec squared is 1 plus tan squared. I could substitute that in. Tan squared minus tan squared is 1. So I know that. Tan theta cos theta, I see something like that. Oh, hang on, there's no squares in there. How would I use a trig identity? I find a lot of the time, if I've got a trig identity question, which I'm just going, oh, how do I prove this? What do I do? If I can't see it straight away, I go, oh, let's just bring everything back to sine and cosine and play with it. That's where the relationship comes in handy for this one, because I go, well, tan theta, I could change that to sine on cos. And then the cos cancels, and I just get sine theta. So really those three examples just illustrating the idea of thinking of, okay, look for the square, which identity. If I haven't got a square, maybe I'm just going to use that nice relationship where I turn everything into sines and coses. This is more like what we're going to see. Prove this. So we're going to do a proof. 2 sec squared alpha minus 2 over 4 tan alpha is tan alpha on 2. And there are different ways we could approach this problem. I'm going to start with the left-hand side. Now you'll notice I didn't write left-hand side equals, which I know some people are obsessed with writing down, and I never understand why. I know my left from my right. You don't need to tell me that's the left. Just write down what it is. The left-hand side is 2 sec squared alpha minus 2 over 4 tan alpha. The only thing I can use in a proof is something that I know is factually true. So alright, what do I know is factually true if I want to transform this equation? I see the square. Okay, I know sec squared is 1 plus tan squared. I'll substitute that in. I know this is a true statement. That is indeed the same as the other one, no matter what. Let's tidy it up, and eventually, oh look, we've got some tans cancelling, the 4 and the 2 cancels, and I get the right-hand side. And again, I don't need to say equals the right-hand side. I mean, it is the right-hand side. I don't need to say that, because I have proven what they've asked. I started with this, I ended with this. That is what they asked me to do. I said there were different ways we could do it. I started with the left-hand side and went and proved it was the same as the right-hand side. I could have equally started with the right-hand side. There's nothing that says you have to start with the left-hand side. You're just showing two things are equal. So I could start with the right-hand side and go prove it's the same as the left-hand side, and sometimes that might be easier. The other way of doing it, of course, is I'll just work on them independently and show that they both equal the same thing. And if they both equal the same thing, therefore they must be equal to each other. That's a third way of approaching it. But never ever solve it like an equation, because it's not an equation. We do not know this to be factually true. We're trying to prove it is. So to get this and do as a first step, oh, let's get rid of the denominators and I'll multiply everything by 2 and then I'll multiply everything by 4 tan. You can't do that because you don't know those things are equal. You're trying to prove they're equal. You're not solving an equation. What if I had started with the right-hand side? Okay, tan alpha on 2. Gosh, what am I going to do? I know I need to get the trig identity in there. The advantage with a proof is you know where you're heading to, you know what the answer to look like. So in this case, I'm not going to change the tan into sine on cos, because when I look at what I'm trying to prove, there is no sine and cos. That doesn't seem like a good way to go. The trig identity, let's force it in there by multiplying top and bottom by tan alpha. That forces a tan squared now. And then that tan squared, I can write as sec squared minus 1. Okay. Well, now I just multiply top and bottom by 2 and I've got the left-hand side. Now that's probably not the best way of approaching that, but of course you could do it that way. There's nothing stopping you. Another idea, changing what it is that you're going to prove. Now I said you can't treat it like an equation, and I'm not here. What I'm doing is I'm changing what it is I'm trying to prove. So I'm saying instead of trying to prove the left-hand side equals the right-hand side, I'm going to try and prove the left-hand side minus the right-hand side is equal to 0. Because if I can show that is factually true, once I know it's factually true, then I can treat it like an equation and I can move that term to the other side. And therefore I've got the proof that this equals that. This idea actually is very common when you're actually doing inequalities. Because sometimes it's easier to show something's always positive or something's always negative than trying to show one thing's bigger than another. It's a common idea for that one. But alright, start with the left-hand side of this. I want to try and show this is equal to 0. That's what I'm attempting to prove. But always write down what you're attempting to prove, because someone is going to read your proof. Now if I'm changing what I'm trying to prove, they need to know what is it you're attempting to do? Because when you say, oh look, I've done it, they're going to, done what? You didn't tell me what you were trying to do. So always write down, if you're going to adjust it, this is what I'm attempting to prove. It's now like an algebraic fraction. Let's pull it into an algebraic fraction. Now, the top of the fraction, 2 sec squared minus 2. Well, if you don't see it straight away, sec squared I can change to 1 plus tan squared. But you might see this sec squared minus 1 is the same as tan squared and go straight to that. But now when I play around with it, sure enough, the numerator turns out to be 0, so the whole fraction turns out to be 0. So what I have just done is, yeah, okay, I've proven this, but now I know that that is factually true. I could move that tan alpha on 2 to the other side and it will still be true. There's my proof. Alrighty, so that shall start us off for the term. So 6F and 6G.